From massive hammers to precision simulations, these are the top 5 fortune solvers shaping the industry. But what if you could build one by yourself? Deform 3D 2D. Estimated market share 35–40%. One of the most established tools for metal forming, widely used in automotive, aerospace, tooling, and extrusion industries, known for robustness, comprehensive material libraries, and detailed process chain modeling, including die wear and thermal history. Highlights implicit FEM with adaptive remeshing, no ALE. Number 2. Semi-fact forming. Estimated market share 12%. Part of the simulation MSC hexagon ecosystem, used in multiphysics forming when thermal mechanical microstructural effects matter. Unique for using finite volume method in 3D, whereas in 2D is finite element. Number 3. Q-form. Estimated market share 15%. Great for workflows where simplicity and stability are key. Growing popularity in die forging and forming with complex contact. Highlights Lagrangian FBN approach. Simpler user input and geometry handling, often used in Eastern Europe and Asia. Number 4. Forge NXT, X-Forge. Estimated market share 25%. A European favorite, especially strong in closed-die forging and multi-step processes, frequently used for tool life, grain flow, and thermal management. Highly visual, clean interface. Highlights implicit FEM, very refined post-processing, ideal for complex multi-pass forming routes, supports for forging, rolling, and ring rolling. Number 5. AFVEX. Estimated market share 3–5%. Mostly used in academic research and small industrial setups. Very solid for cold forging with clean UI and decent material handling. Implicit FEM with adaptive remeshing. Highlights. Quick setup for axisymmetric and 2D plane strain problems. Useful for educational rapid concept validation. Export results for paper-ready plots. In forging, unlike high-speed impacts or crashes, deformation usually happens slowly enough that dynamic effects like inertia are often negligible. So, most forging solvers simplify the problem by treating it as quasi-static or pseudo-static. That means they focus on equilibrium at each step without accounting for acceleration forces. Implicit methods solve the problem step by step, assuming slow deformation, which helps reduce computation time while keeping results accurate for typical forging speeds. Explicit methods naturally include inertia and dynamic effects because they compute how things move in small time increments. Almost all solvers rely on tetrahedral elements because they handle complex geometries and automatic meshing well. Most FEM solvers use reduced integration, typically one-point integration per element, to reduce computational cost. But this comes with challenges like hourglass modes that require stabilization. Mesh treatment. Lagrangian Eulerian. Most FEM solvers use an updated Lagrangian approach where the mesh moves with the material, updating configuration each time step. Semi-factant use Eulerian or ALE approaches, allowing the mesh to stay fixed or partially moved. While these solvers are impressive, I've been building something new, a forging solver from scratch. I'm currently migrating everything I've learned from explicit solvers like time derivatives, remeshing strategies, and contact algorithms into a new updated Lagrangian pseudo-static solver written in modern C++. It is designed with future CUDA support in mind, and I am integrating Eigen and potentially PETSc mathematical libraries for efficient linear solvers. The goal? A fast, open-source forging simulation tool built for real-time insight into metal forming processes. I will be sharing every step as this solver comes to life. If you're into open-source mechanics, you won't want to miss it. If you're into FEM, SPH, CFD, remeshing, or just enjoy watching solids get squished by clever math, you're in the right place. I dive into open source solvers, GPU acceleration, and how these methods actually work under the hood. So hit subscribe, or better, hop on the mailing list at opensourcemag.com. No spam, just good stuff. And if you want to support or ask deeper questions, there's always my Patreon. Thanks for watching and happy coding.